Sir, you may start your lecture.
Respected coordinator, madam, principals, and children, welcome back to the webinar sessions for second year intermediate. I am here to present you the webinar session for physics, unit 5, part 1, electrostatic potential and capacitance, part 1. I am N. Subramanyam, PGT Physics, TSMS, M. Turkapalli, Yadadri-Bongir district. A warm welcome to all of you, all the students who are listening to this webinar. Let us move on. Till now, children, already in this webinar series, I have presented unit 4, that is electric field and charge, that is electric charge and field. So I hope all of you are ready for the unit 5. Shall we start, children? Okay. So the learning objectives for this particular webinar session. Introduction for this particular unit. Electrostatic potential. Potential due to a point charge. So these are the learning objectives. I will be introducing the concept of electric potential and the importance, and we will also look at a derivation, potential due to a point charge. And this lesson is very important both from the public exam point of view as well as all the entrance examinations point of view. In each and every entrance examination, you will certainly get questions from this particular topic. So let's move on and let's look at the discussion. I would like you to recall the following points which were dealt in unit 4. The first one, the expression for unit, the intensity of electric field. E bar is equal to 1 by 4 pi epsilon 0 q by r square. This is the expression for intensity of electric field due to a charge q at distance r from it. The second point, the force acting on a unit positive charge or the force acting on a positive charge q naught at a point in the electric field with intensity of electric field E bar at that point in the electric field is F is equal to q naught into E. Here F is a vector, E is also a vector. I have shown them by using the bar symbol, which you all know. Okay. So the next point. Now let us go straight into the lesson, children. What do we see on the screen? Yes, a charged body and the electric field depicted by using the oval here. For our convenience sake, we are using such a region. Okay. So this region is the field around that particular charge, electric field of this particular charge. So you are seeing that every charged body can create an electric field. Let it be positive charge or let it be negative charge. Please recall that they can create an electric field. So in this electric field, already we learned that. So let us say if there is a charge plus q and around that there is a electric field of that charge. In this particular field, I am choosing a number of points. Let us say this point, this point, this point, so on. So for each and every point, there is some field value and there is a particular direction. So the field at the, this point is E1 bar. At this point it is E2 bar. At this point it is E3 bar. And the directions indicated by the red color arrow. So if you see carefully, In this particular picture, I am showing you that the electric field is depicted in terms of vectors because electric field intensity is a vector quantity. That means the characteristics of that field are studied by using the vector electric field vector. Okay, so this is how we are characterizing the field in this particular picture. Now the question arises, if I want to study about the characteristic of the electric field in terms of the scalars, is there a method? That is the question. So for that, let us move on and see whether we get the answer. Okay. So electric field intensity is a vector quantity that we all know. Let's move on. Now the same electric field I am showing here, but I have symbolized by certain symbols V1, V2, V3 like that. So what are these V1, V2, V3? They are nothing but the electric potentials at these particular points. That means for the same points which I have shown earlier, if you see here, for the same points I am showing you here the potential values. So this potential at this point is V1, here it is V2, here it is V3. So what is the importance with this discussion? This V1, V2, V3, all these things are scalar quantities. That means electric potential is a scalar. That means in the earlier picture, I have talked about the electric field in terms of vector values. Now in this picture, I am talking about the same electric field in terms of scalars, that is V1, V2, V3. So this particular notation helps me to talk about the electric field in terms of scalar quantities because electric potential is a scalar quantity. This please remember. I will again come to the same point when we discuss in detail about electric potential. So now we understood that the electric field can be characterized in terms of vectors or characterized in terms of scalars. If we want to talk about the characteristics of the electric field in terms of vector quantity, we use electric field intensity. If we want to characterize about the electric field in terms of scalar quantities, we use potential, potential energy, all these things. So I hope you followed. You will know more about it as we move on. Okay. So let me go into the topic straight. If you see on the screen, I am showing you a ball placed on the floor. Now you all know this example which you studied in first year. If I lift this ball to some height, what will happen? It will gain potential energy. Can you tell me how this body is gaining potential energy, children? Can you tell me? Did you study in first year? Yes. When this ball is lifted from ground level to this height, we are doing work against the gravitational force. Whatever work is done against the gravitational force, that is getting stored as potential energy. The work done against the gravitational force in lifting the body is stored as potential energy. So work done against a gravitational force is stored as potential energy of the body. I hope you understood. So this concept is important, children. Work done against the gravitational force is stored as potential energy. Please remember this because this has got some link with the present discussion which is going on. Now again I am showing a spring. This is familiar example to all of you, yes or not? The spring is, if you see in the picture, it is getting compressed, it is getting elongated. And whenever it is compressed or elongated, there will be some energy stored in it, potential energy stored in it, which you studied in your first year intermediate. Yes or not? So, work done against the spring force is stored as potential energy. So now I have told you two examples, children. In both the examples, work was being done against some force. That particular work done against the gravitational force got stored as potential energy. Similarly, work done against the force got stored as potential energy. So let you do one more. Before that, you see carefully. Gravitational force, spring force, Coulomb force between two charges are conservative forces. So let me explain. So the gravitational force, spring force, Coulomb force between two charges are conservative forces. What is the meaning of conservative forces? You studied in first year intermediate, yes or not? So you will be looking at the same type of conservative forces here also. So gravitational force, spring force, Coulomb force, they are all conservative forces. What is the link between this point and the discussion? Let us see. Similar to potential energy of a mass in a gravitational field, we can define potential energy of charge in electric field. So we saw just now work done against the gravitational force that is getting stored as potential energy. Similarly, we can define potential energy for electric field also. So just like a mass has potential energy in a gravitational field, a charge can also have potential energy in an electric field. Let us see how we can define. Okay. So for that purpose, I am using this example. On the screen, what are you seeing? You are considering a charge plus Q. Okay. Now this is the electric field of the charge plus Q. Okay. So this is the electric field of the charge plus Q. Now I am taking a point P inside the electric field. Consider this point P. Similarly, consider another point R in that electric field. Now I kept one charge plus Q here at the point R. Okay. So again see carefully. On your left of the screen, what is there? There is a charge plus Q. And inside that electric field, how many points are being considered? One is a point P, one is a point R. Okay. And I kept another charge plus Q. This is small q. Okay. At this point R. Now tell me all of you. This is plus Q, this is plus capital Q. Both are positive. Is there any repulsion between them? Yes. Definitely there will be some repulsive force between them. So that is a force shown by this red arrow. And it is pointing away from the charges. So let us call the repulsive force as Fe. E for electrostatic. Okay. Electrostatic force of repulsion. And now we are very clear that plus Q and plus Q are repelling each other. This plus capital Q and plus small q are repelling each other. Now, I am moving this plus Q from capital R to capital P points. From where to where, children? From point R to point P. So now tell me all of you, to move this small q charge from R to P, I should do some work against the repulsive force, because what will happen? You think, you apply your logic, all of you. This plus q, this capital plus q charge, will it allow the small plus q charge to come closer to it? No, because we already saw that there is some repulsion. That means even though there is some repulsion, I am moving it from one point to the another point by overcoming this repulsive force. That means work is done against the repulsive force. So, as per our earlier discussion, when the work is done against the conservative force, that is stored as potential energy. Yes or not? That means if you see here, it is moved from here to here. So the work done in moving plus Q charge from point R to point P increases its potential energy. Yes or not? Increases its potential energy. It is gaining the potential energy. It is gaining the potential energy. Just like when the mass is lifted from one point to the another point against the gravitational force, it is increasing its potential energy. Yes or not? Similarly, here also, work done in moving plus Q charge from point R to point P increases its potential energy. So the work done to move the charge is WRP is equal to delta U is equal to UP minus UR. So these are familiar symbols to all of you. Yes or not? Here delta U denotes the increase in the potential energy. UP is the potential energy at the point P. UR is the potential energy at the point R. So here delta U is UP minus UR is the difference in the potential energy between points R and P. So here UP minus UR difference, minus sign always means what? Difference. So here UP minus UR is symbolizing the increase in the potential energy as is shown in the first point. Okay, so here increase and difference are one and the same. Okay, so let me move on. Please keep that in mind. Now let us define something called as electric potential difference, Vp minus Vr. That is a potential difference between the points P and point R. Here Vp denoting potential at the point P, Vr denoting the potential at the point R. So Vp minus Vr is the potential difference. So how do we define this potential difference? Let us try to understand. So Vp minus Vr is actually equal to Up minus Ur by Q. By Q, that means the difference in potential energy per charge. That is the potential difference. So see carefully children, Vp minus Vr is what? Potential difference. This potential difference, how you must calculate? The difference in the potential energy, Up minus Ur by charge Q. And already you have seen that Up minus Ur is equal to WRP. So substituting that value, I get WRP by Q. So it is a work done in moving the charge from R to P by charge Q. Okay. So Vp minus Vr is equal to WRP by Q. So potential difference is the work done per unit charge in moving from R to P. Per unit charge I can tell. By charge means per unit charge, no. Yes or not? So I hope you followed. Let us see what is the connection between this and the actual potential value. Okay. So if we choose a point R such that R is at infinity and potential at infinity as 0. So now what we are telling? Consider that R is at infinity. And if R is at infinity and potential at infinity is taken as 0, that is Vr is equal to 0, then what happens? Vp minus Vr becomes Vp minus 0 in our earlier formula. And that becomes equal to W infinity to P by Q. Here earlier what was there? See, what was there here? Vp minus Vr is equal to Up minus Ur by Q. Now this Vr is taken as 0 and this R is at infinity now. That means Vp minus 0 is equal to W infinity to P by Q. So that is what I am telling here. See here. Okay. So I suppose I am clear with the equation what I am writing on the screen. Vp minus 0 is equal to work done in moving the charge from infinity to P by the charge value. That is work done per unit charge. Okay. So Vp minus 0 is how much? Vp. Vp is equal to W infinity to P by Q. So I can tell now clearly that Vp, what is Vp? I told you the potential at the point P. The potential at the point P is equal to the work done per unit charge in moving the unit positive charge from infinity to the point P. So this is the definition for potential at the point P. So that is now the definition for potential at point P. So electric potential at a point, how do we define? Let us say the point is P. Learn the definition, children. The electric potential at any point P is the work done in bringing a unit positive charge from infinity to point P in the electric field. So the electric potential at any point P is the work done in bringing unit positive charge from infinity to point P in the electric field. So unit positive charge means how much? 1 coulomb of charge. Okay, how many coulombs of charge? 1 coulomb of charge. So work done per unit charge means, that is the meaning of that. It is nothing but equal to work done in bringing the unit positive charge. So unit positive charge, the word unit positive charge, we have come across this in the first year in the unit 4 topic. Unit positive charge means how many coulombs? Plus 1 coulombs. So if I bring a unit positive charge from infinity to the point P, the work done in the process is itself equal to the electric potential. So this please remember. So Vp is equal to W infinity to P by Q. So when I divide the work value by the charge value, I will get work done per unit positive charge. So please remember this expression. We will be using it a little later in our lesson. So let me move on, children. But if you see this expression carefully, nowhere this formula is having distance. Yes or not? That means this expression is useful when you know the charge being moved. But if I am trying to derive a formula for the electric field potential, okay, formula for the electric field potential in terms of the distance, then how I should do it? That is what is my question. So let us try to learn that one. Let us see. For that, before I go to that, a small point. Electric potential at any point is a scalar quantity, and the SI unit of electric potential is joule per coulomb, which is written as JC inverse. Okay, and joule per coulomb is known as volt. Symbol is capital V. I hope you understood. The potential at any point is measured in volts. Okay. So now an important derivation for your public exam. So please be attentive and practice this derivation as many times as possible. Okay, and become perfect. So let us see potential due to a point charge. Okay. So this is the point charge what we are considering, plus Q. Okay, this is the point charge what I am considering. Now this is the electric field of this point charge. This is the electric field of this point charge. Okay, and in that electric field I am considering a point. Point is P. Okay, my ultimate derivation is finding the potential at this point P. That is the work, that is the derivation what I have to do. Remember, finally what I have to calculate? I am potential at the point P. Okay. For that purpose, I am considering another point, children, P dash inside the field. So now see carefully. P is one point in the field. P dash is another point in the field. What is the distance of P from the charge? R. Similarly, distance of P dash, R dash. Okay, see carefully. P distance is R from the charge. P dash distance is R dash from the charge. Now I kept unit positive charge. Unit positive charge means what is the meaning I told you? Plus 1 coulombs. Okay, plus 1 coulombs. This plus 1 coulombs charge, let us say, when I kept here force on it, let the repulsive force is F. Okay, what is the repulsive force on it? F. Why there is repulsion? Very easy to understand. This is plus Q, this is plus 1. Plus and plus charges. Will they attract or repel? They will repel with each other. Okay, now what is my aim? Don't forget the aim. My aim is to calculate the potential at the point P. Okay, so how do I do it? Let us see. So, this plus 1 coulombs of charge at the point P dash, I am slowly moving it by distance R dash against the repulsive force. I am slowly moving it by distance dr dash against this repulsive force. So this plus 1 coulombs of charge you are able to see or not? That I moved by how much distance? Dr dash, small distance, very small distance, children. Very small distance I moved by how much distance? Dr dash against the force. Now to tell me all of you, if I have to move it against the force, I should do some work or not? Yes, definitely I have to do some work. So there is going to be some work done in moving this plus 1 coulombs by this small distance dr dash. So I am going to calculate that value. First of all, force on the unit positive charge at P dash is F is equal to 1 by 4 pi epsilon 0 Q into 1 by R dash square. How did you get this answer? Tell me. Coulomb's law. Do you remember Coulomb's law? F is 1 by 4 pi epsilon 0 Q1 Q2 by R square, where R is the distance of that charge. Now if you see in the earlier diagram, what is the distance here? You see, this is Q, this is 1. So two charges, this is Q1, this is Q2. Q1 is plus Q, Q2 is plus 1. Q into 1 will become Q. Okay, and what is the distance here? R dash. So please remember in the formula, F is equal to 1 by 4 pi epsilon 0 Q into 1 by R dash square, because R dash is the distance between Q and 1. This is according to Coulomb's law. Okay. So now if you simplify that, what are you getting? F is equal to 1 by 4 pi epsilon 0 Q into 1 is Q by R dash square. F is 1 by 4 pi epsilon 0. Q into 1 is Q by R dash square. So now I am calculating the work done in moving the unit positive charge. By how much distance I moved. In the diagram I told you how much distance I am moving. dr dash against the force. Which force? Repulsive force is, let us call the work done as what? dW. dW is equal to minus 1 by 4 pi epsilon 0 Q by R dash square into dr dash. Let me explain this, children. Give me a moment. You remember work done formula in your first year intermediate? Work done is negative if you are moving against the force. So I got negative sign. So I have justified why I got negative. That is the first point. Next, work done formula. Force into displacement. You remember? So that is general definition. As per that, F is a force here. Okay, I wrote that. And displacement how much? dr dash. So dW is equal to minus 1 by 4 pi epsilon 0 Q by R dash square dr. This you can interpret in another manner also. Work done is Fs cos theta. And when F and S are in opposite direction, we have to take 180 degrees. Yes or not? Now if you see in the earlier diagram, F is like this side, and displacement is this side. That means the force is to the right, whereas plus 1 coulombs is displaced to the left. So what is the direction? Opposite direction. When opposite direction is there, what is the angle we will take between force and displacement? 180 degrees. That means cos 180 will become what? Minus 1. So like that also I can explain. So if you see, work done becomes negative. That is dW is minus 1 by 4 pi epsilon 0 Q by R dash square dr dash. So however you explain, you will get the same equation number 1. I hope I have justified. Okay, let me move on. So now in that first diagram, I moved the 1 coulomb charge from one point to another point by small distance dr dash. Yes or not? Now again if you see the diagram, in the same electric field, our point P, which I told earlier, with the distance R. Okay, this point I suppose you remember. Now consider that the plus 1 coulombs is at infinity. And from there, I moved it to the point P. So now tell me again, plus 1 and plus 2, repulsion will be there or not? Yes. Sir, how many times you will tell? Yes. Repulsion is definitely going to be there. That means I am again going to do some work in moving the charge plus 1 coulombs from here to infinity. So let the work done in that process is W. So work done in moving unit positive charge by dr dash already we calculated. Okay. This I need not explain. It is there for you to see according to the equation number 1. Okay. Now let the work done to bring unit positive charge from infinity to the point P is W. So earlier we calculated to move by distance dr dash. That work done is dW. Now the work done for moving from infinity to the point P is W. How will you calculate W? So that is what is the purpose of dW. You studied already in first year intermediate. All of you know, by PC as well as MPC students, that integral dx is x. Like that, if I know dw value, I will integrate dw value in the suitable limits, then I will automatically get w. Yes or not? Then you might get a doubt, sir, what is the purpose of calculating w? Very simple, children. Read this sentence carefully. Work done to bring unit positive charge from infinity to the point P. What is this actually as per definition? If I calculate the work done to bring unit positive charge from infinity to the point P, that is itself the potential, no, as per definition. That means if I know W value, I will automatically know potential value. Okay, so let us see how to calculate W. So W is integral dW. In what limits? Infinity to R. Okay, I will explain in a moment. One minute, children. Okay, so infinity to R dW. So why these limits were taken as infinity to R? Very simple. The charge was initially at infinity plus 1 coulombs. From there it came to the point P. That means the distance is initially equal to what? Infinity. Finally it is equal to R. So the lower limit is infinity, upper limit is R for the integration. So I hope I have given the justification. Now what did I do? I substituted dW value. What is dW value? Minus 1 by 4 pi epsilon 0 q by r dash square. Okay, into dr dash. That I substituted. So let us call that as equation number 2. So let us move on with the derivation. So this is equation number 2 already. Now, just a minute, children. If you see carefully, let the graphic come up. I will explain. Okay. Now you see carefully, children. W is equal to integral dw infinity to r. Yes or not? Now in this, already in the previous equation number 2, 1 by 4 pi epsilon 0 is a constant, no, so keep it outside. Minus anyhow will bring it outside. Q is outside. Then what is a variable which is remaining? R dash is a variable which we are integrating. So 1 by r dash square integral dr dash is the integral which we have to calculate. Now how to do this? Think that r dash is x, children. So this becomes what? 1 by x square dx. Did you not do in your first year intermediate this type of thing? You got in I suppose first year intermediate. In when you are doing problems related, that is derivation related to stress energy. Yes or not? So like that you are doing the integration. That is very easy. How to do this one? If you see carefully, I am now solving integral infinity to r 1 by r dash square dr dash. Now r dash square, if you take to the numerator, it will become r dash power minus 2. So 1 by r dash square integral dr dash will be equal to minus 1 by r dash in the limits infinity to r. Just a minute, children. If you see carefully, this one, this integral will be 1 by r dash square integral dr dash. Yes or not? That how I am writing r dash power minus 2 dr dash. Okay, integration in the limits. And this you have studied already. X power n dx formula. X power n dx formula is what? X power n plus 1 by n plus 1. That means r dash power, here r dash power minus 2 plus 1 by minus 2 plus 1. So r dash power minus 2 plus 1. What will it be? R dash power minus 1. And here also it will be minus 2 plus 1 minus 1. So minus 1 r dash, this is r dash power minus 1 by minus 1. So minus 1 divided by minus 1 means here minus. See here, this is the minus. And this is r dash power minus 1. If I bring it to the denominator, what will I get? 1 by r dash. That is how this I got. Okay. So 1 by r dash in the limits infinity to r is equal to. And how will you substitute the limits? First I have to substitute upper limit. So in the place of r dash, what is this upper limit you see? R. So I am substituting r. So I will get minus 1 by r minus 1 by infinity. Now I am substituting lower limit in the place of r dash. This 1 by infinity, it is nothing but 0, because you all know 1 by infinity is what? 0. So 1 by r minus 0 will become 1 by r. That means finally I am left with what? Minus 1 by r. So this total integration value is nothing but minus 1 by r. Okay, all of you? I suppose I am clear. Okay, let me move on, children. So this already we saw. So as infinity to r, 1 by r dash square is minus 1 by r. This if I substitute here, I will get, you see the substitution. You see the substitution, children. This integration substitution is minus 1 by r. Okay. This minus 1 by r, if it goes here, minus into minus. This minus into minus will become plus. Q into 1 is Q. That means what is the work done value? 1 by 4 pi epsilon 0 Q by R. Okay. So the work done is equal to 1 by 4 pi epsilon 0 Q by R is the final value of the work done in moving the charge from infinity to the point P. What charge? Unit positive charge. So that is important. Equation 4. Work done in moving infinity to the point. So this is infinity to the point P. Okay. So equation 4 gives us the work done in bringing a unit positive charge from infinity to a point P in the electric field, which is by definition equal to the potential at the point. So that means that this work done itself is equal to the potential. Therefore, potential at the point P is V is equal to 1 by 4 pi epsilon 0 Q by R. Q by R. So this is the final expression for potential, children, in terms of the distance. In terms of the distance. In the earlier expression for potential, we were not having distance. It was in terms of the work done. But now you see this expression, it is in terms of the distance. Yes or not? So now we are having two expressions for the potential. One in terms of the work done, one in terms of the distance. So as per the given situation, whichever is necessary for doing the problem, you can use that. Okay. So in your entrance examinations, you will get number of questions based on potential calculation. This is the expression you can use for that. So to explain that, I am using some numerical examples for you. Let us see those numerical examples. The first one, and before I go to that, potential at the point P is V is equal to 1 by 4 pi epsilon 0 Q by R. And I would like to tell you two important points before I go to the numericals. Number one, potential due to a positive charge is positive. Number 2, potential due to a negative charge is negative. So this is important. Potential is scalar quantity, no. So if there is a positive charge, it will create positive potential. If there is a negative charge, it will create negative potential. That is the meaning of this. So to make you understand these points more clearly, I will teach you some numerical examples. And before that, I will tell you how to calculate the potential due to a system of charges. Okay. So in this particular screen, you are seeing that there are a number of point charges. Let us say Q1, Q2, Q3, Q4, so on. And there is a point P. So I want to calculate what is the potential at the point P. Okay. So what is the distance from Q1 to P? R1. Q2 to P, R2. Q3 to P, R3. Q4 to P, R4. Remember, these are the distances of the point charges from the point P. Okay. So I want to know what is the potential at the point P due to all this system of charges. Now, very simple to remember. You remember in electric field, when more than one charge is considered, each charge will create a field. Similarly, here how many charges are there? Every charge will create potential at this point. Okay, every charge will create potential at this point. So Q1 will create potential V1 at this point. Q2 will create potential V2 at this point. Q3 will create potential V3 at this point. Q4 will create potential V4 at this point. That means the total potential by the superposition principle is the potential at the point is V is V1 plus V2 plus V3 plus V4. That is 1 by 4 pi epsilon 0 Q1 by R1 plus Q2 by R2 plus Q3 by R4 plus Q4 by R4. I took 1 by 4 pi epsilon 0 common. And what is the formula I used? I used the formula which we got earlier. What is the formula? V is equal to 1 by 4 pi epsilon 0 Q by R. Okay. So, just a minute, children. So, you remember? This is the formula, what we have used. 1 by 4 pi epsilon 0 Q by R. Okay. This formula, how many times I am using? 4 times for 4 different potentials. And I got the total potential. The total potential is just algebraic sum of all the potentials. Okay. So, I hope I am clear. Let me move on. The first numerical example. Find the electric potential at a distance of 10 centimeters from a charge of 10 microcoulombs. Okay. Simple example to start with. Let us see the solution. Charge Q, how much? 10 mu c. 10 into mu c means, you know, no, I taught you in the unit 4 also, microcoulombs. Micro means how much? 10 power minus 6. Next, distance from the charge R, how much? 10 centimeters. Next is equal to centimeter, convert into meters children. What should we do? We learned already. Multiply 10 power minus 2. 10 into 10 power minus 2. What will it become? 10 power minus 1 meters. What is the question given to us? Potential due to the charge is V is how much? Very simple question to start with. Just apply the formula, get the answer. That means I want to make you use the formula so that it goes into your memory and it gets drilled into the memory. Okay. So formula, tell me what is the formula for potential when charge is given and distance is given? Right, 1 by 4 pi epsilon 0 Q by R. So V is 1 by 4 pi epsilon 0 Q by R. Now again let us see. V is equal to, what is the value of 1 by 4 pi epsilon 0? 9 into 10 to power of 9 into Q value 10 into 10 power minus 6 by R value 10 power minus 1. I hope this substitution is clear. This is 1 by 4 pi epsilon 0. This is Q value. This is R value. What is 9 tens are? 90. 10 power 9 as it is. In the bracket 10 power minus 6 by 10 power minus 1. What is 10 power minus 6 by 10 power minus 1? 10 power minus 5. Yes or not? Simplification. This type of simplification you know, easy. 90 into 10 power 9. 10 power minus 6 by 10 power minus 1 is 10 power minus 5. 10 power 9 into 10 power minus 5. When bases are same, powers add. 9 plus 5. That is 9 plus minus 5. 4. That means final answer V is equal to 90 into 10 to power of 4 volts. Okay. I used the symbol for volts. I hope the answer is clear. One more numerical. Let us see. Second example. Find the electric potential at a distance of 10 centimeters from a charge of minus 5 microcoulombs, mu c. Let us see the solution. First, the charge value. Q is 5 mu c. Minus 5 into 10 power minus 6 coulombs. Distance R, okay, from the charge. How much is the distance? Here you see, read the question once again, 10 centimeters. So 10 centimeters. Again convert into meters. 10 into 10 to power of minus 2 meters. Conversion factor. What is 10 into 10 power minus 2? 10 power minus 1 meters. Okay. Potential due to the charge is V is equal to how much? That is the question. Now how to solve this question? Again apply the formula. V is 1 by 4 pi epsilon 0 Q by R. Okay. Because Q is given, R is given. Let us see. First V is 1 by 4 pi epsilon 0 Q by R. V is 9 into 10 power 9. 1 by 4 pi epsilon 0 directly substitution. Q value, be careful, minus 5 in 10 power minus 6. That's what I was telling. Positive charge, positive potential, gives positive potential. Negative charge gives negative potential. That is the reason why Q, if it is negative, substitute negative value. R, 10 power minus 1. What is 9 5s are? 45. That means 9 into minus 5, minus 45. Simplification. Minus 45 into 10 power 9 and 10 power minus 6 by 10 power minus 1. Again, what is 10 power minus 6 by 10 power minus 1? I told you once, 10 power minus 5. So here what you are having, you see, minus 45 as I told you, 10 power 9. So simplification, minus 45 and 10 power 9 into 10 power minus 5. 10 power 9 and 10 power minus 5, what will it become? 10 power 4. So V is equal to minus 45 into 10 power 4 volts. See the final answer? Negative. That means potential can be positive, potential can be negative also. But in electric field, you will never get negative answer. Answer is always positive. Only the direction will change. Yes or not? So that is a basic difference between electric field question and potential question. When you are calculating electric field values, you will always get final answer only plus, and you will also add direction to it because it is vector quantity. But in potential, you see, you can get final answer negative also. So don't think that you are doing wrong if you got negative answer. Potential can be negative also. Okay, depending on the given charge value. If it is positive charge, you will get positive potential. If it is negative charge, you will get negative potential. Okay, very important, children, because many of our children are attempting entrance examinations. They should remember this point. You are going to get number of questions in your entrance examinations where calculation of potential is required. There it is very useful to you. Okay, let me move on with one more example. Example number 3. 2-point charges QA is equal to 3 microcoulombs and QB is equal to minus 4 microcoulombs are located 20 centimeters apart in vacuum. What is the electric potential at the midpoint of the line joining the two charges? Same type of question I have discussed in unit 4 for calculating electric field. Now again same type of question I am discussing for calculating electric potential in this unit, children. See the answer. Please revisit your webinar session and see the answer variation there and here, how we are doing. Okay. I request you that all of you just visit the webinar sessions for unit 4 also. In that, a similar problem is there for electric field calculation. Here I am doing electric potential calculation. Let us see what is the answer we are getting, how we are doing. Okay. How many charges? 2 charges. Okay. Separated by how much distance? 20 centimeters apart in vacuum. Let's see the solution. First see the graphic. 2 charges QA, QB separated by some distance. And at the midpoint P, I want to calculate potential. Okay. So QA is 3 mu C. QB is minus 4 mu C. Distance of the midpoint is R is equal to 10 centimeters from each charge. Because it is midpoint, total is 20. Potential and midpoint is how much? This is the question. Okay. For getting the answer, let us see what is the solution. Now the graphic you see. 20 centimeters total distance, midpoint is P. QA will create potential VA at this point. QB will create potential VB at this point. That means at the point P now how many potentials are getting created? 2 potentials, VA and VB. And no need for directions. No need at all for directions, children. When you are having potential, you need not worry about direction. It is a scalar quantity. Just calculate the value of VA and VB and proceed to calculate total value. Total means algebraic addition. Okay. So I will tell you how to do it by this example. Let us see. Solution, let us continue. QA is equal to 3 mu C. 3 into 10 power minus 6 coulombs. QB minus 4 mu C. 4 into minus 4 in 10 power minus 6 coulombs. R is 10 centimeters. 10 into 10 power minus 2. Why did I do 10 in 10 power minus 2? Yes, converting centimeters into meters. That is 10 in 10 power minus 2 is 10 power minus 1 meters from each charge. Potential at midpoint V is how much? Tell me what is the formula we must use? Remember? Yes. V is 1 by 4 pi epsilon 0 Q by R. That formula you must use 2 times. Once for calculating VA, once for calculating VB. So V is 1 by 4 pi epsilon 0 Q by R. First calculate VA, children. 1 by 4 pi epsilon 0 is 9 in 10 power 9. Q, first charge value how much? 3 in 10 power minus 6. By distance, 10 power minus 1. What is 9 threes are? 27. 10 power minus 6 by 10 power minus 1 is remaining. What is 10 power minus 6 by 10 power minus 1? If you see here, 27 into 10 power 9 into 10 power minus 5. 10 power 9 and 10 power minus 4, 5 will become 10 power 4. Okay. So the value of potential here is VA is equal to, what is the value? 27 into 10 power 4 volts. Wantonly I kept plus sign here to make you understand that QA is positive charge, so positive potential. Okay. Let me move on. So I got VA value already. I need not explain this further. Now VB value. VB is 9 and 10 power 9. That is 1 by 4 pi epsilon 0. Same formula, use it second time. QB value minus 4 in 10 power minus 6 by 10 power minus 1 is equal to simplification. I suppose I need not explain now. You have followed. What is the simplification? 9 into minus 4 minus 36. Very good. Then 10 power minus 6 by 10 power minus 1 in the bracket. 10 power 9 as it is. Okay. This simplification how much? Tell me. 10 power minus 5. 10 power minus 5 into 10 power 9 will become 10 power 4. So minus 36 into 10 power 4 volts. See the value carefully. Minus charge, minus potential. Plus charge, plus potential. So the final value, electric potential at midpoint is V is addition of VA and VB. 27 in 10 power minus 4 plus minus 36 into 10 power 4. So I suppose this is VA plus VB. I told you no superposition principle. When number of charges are there, you add all the potentials due to each and every charge. Then you will get total potential. So V is the total potential. VA plus VB plus so on. And remember children, that can be used for any number of charges. Here I used only for 2 charges. Now simplification is very easy. 10 power 4 is common. 27 plus minus 36 will become minus 9. So minus 9 into 10 power 4 volts is the final answer. So I suppose all the theoretical points and problem solving points are clear to you. That brings me to the conclusion of this session. Let me see what we have learned. First point, electric potential at a point Vp. What is the definition? The electric potential at any point P is the work done in bringing unit positive charge from infinity to the point P in the electric field. Next point, V is the potential at point P is, as per the definition, W infinity to P by Q. Work done in bringing unit positive charge from infinity to point P. Okay, per unit charge. Okay. Next point, potential due to a point charge at any point P in its electric field is V is equals to 1 by 4 pi epsilon 0 Q by R. To test your understanding, here are a few questions which are also important from exam point of view, public exam. First one, define electric potential. Second one, derive an expression for the electric potential due to a point charge. The derivation we did, no integration derivation, that is important for exam. Please learn it carefully. Okay. The next one simple problem. Find the electric potential at a distance of 20 centimeters from a charge of minus 10 microcoulombs. Find the electric potential at a distance of 20 centimeters from a charge of 10 microcoulombs. So that brings me to the end of this webinar session. I thank my coordinators, Salja madam and Manjari madam, for all the support. I thank my parent department for giving me this opportunity. Thank you for this session.
Thank you, sir. It was a wonderful session.
Thank you, ma'am.
We have either 2 lessons in electric potential.
2 lessons, madam.
Yes. Children, hope this video is very interesting. This lesson, sir, introduction about electric potential. Hope it is very interesting. Once again, go through the lesson and make your notes and try to attempt the problems. Numericals, derivation and numericals are very important. Please understand the concept very well. Thank you very much. Thank you.